Hi guys, day 7 of Unit 1, and we were talking about inverses of functions, which is probably a term you've heard of before. Not sure if you've ever actually calculated one, but should at least sound somewhat familiar. So our first example kind of shows you what an inverse is. So you have f of x equaling 3x plus 7 over 2, g of x equals 2x minus 7 over 3. So these are the two little functions you're being given. So it just asks you to evaluate. So f of 5, if you plug in 5 here, we get 3 times 5 plus 7, and then over 2. So you're just evaluating. So 15 plus 7, that's going to give us 22. Over 2, you should get 11. Then it asks you to calculate g of 11. All right, if we plug in at 11, we get 2 times 11 minus 7 over 3. So that's 22 minus 7, which is going to bring us back down to 15. And then the answer is 5. The next one, you have a composition of functions. So if we do g of negative 1, plug a negative 1 in, we would get negative 2 minus 7, which would be negative 9 over 3 or negative 3. And then you take and you keep going with that value. That's a composition. So get one answer, plug it back in. So now if we do f of negative 3, let's see, that would give us negative 9 plus 7, which is simply just negative 2. And then over 2 would come back to negative 1. All right, so there's that. The last one, where it looks like golf, we know that's another composition. So g of f of 5. But if you look, you already did f of 5 in example A. That came out to be 11. Now if we do g of 11, that you already did, comes back to be 5. So what you might start seeing is in these last two examples, here you start with negative 1, you get to negative 3, you plug in negative 3, it takes you back to negative 1. The last one, you plug in a 5, gives you 11, take that 11, plug it into the other function, comes back to 5. So how these are an example of inverses is anytime you have an inverse function, it essentially undoes what the other function does. So when it's saying without calculation, what would you expect f of g of pi to be? Well, g of pi is going to come out who knows what. But when you plug it into that answer into the f function, it should undo what you had, and it should come right back to pi. So when you think inverse operations, typically, addition and subtraction, those are inverses of one another. Multiplication and division, squaring and square rooting, they all are the opposite operation, or they undo the original one that we're talking about. So here, when it says that two functions from the warm-up are called inverse functions because they blank each other, we're simply going to say because they undo each other. So whatever the one function does, the second one brings you right back to where you started. Right? So here visually, they kind of show you that if you were to take and plug in A into the f function, and it gives you out some particular value b, if you then take that b and plug it into the g function, it brings you right on back where you started. So no matter what you plug in, by doing both of those things, so it's like saying add 5 and then the other function subtracts 5. You'll always come back to where you started. Mm-hmm. So down at the bottom, maybe if you have a highlighter, you can just underline. It has some reminders in here. It says recall that a relation, right? Relation is any pairing of the elements in one set, the domain, with the elements of the second set, the range. So it's any pairing, right, of the elements from the domain to the range, right? It's saying the elements of the domain are called your inputs, the elements of the range are called your outputs. We know that. A function is a special type of relation that pairs every input with exactly one output. So this we know. Then we talked the other day about a one-to-one function, right? And that's where no output is used more than once, right? In the function's pairing. So no repeated y's. That's basically what that one's talking about, right? So an inverse relation, saying reverses the pairings of the relation. So if a relation pairs an input x with an output y, then the inverse is going to do the opposite. It pairs the input y with the output x. So the inverse of a function may or may not be a function itself. And that's what we're going to look at a little bit. If the inverse of the function also happens to be a function, it is called an inverse function and is written as f inverse. That's how we'd read that little guy right there. So I'm going to write that down at the bottom. So if I have f with that little -1 of x, that is read as f inverse. And if it turns out that the inverse is not a function, like it won't pass the vertical line test, whatever, then it's simply we call an inverse relation. So you go back to that more generic labeling. So instead of a function, it'd be an inverse relation. So when we flip it on over, we will look at a couple of examples dealing with this. So the first one, here we go, says the mapping diagrams show a function and its inverse. So they give you a little bit of both here. It says complete the diagram for the inverse of the function. So here's the original function. So since I've got my highlighter, I might as well highlight it there. It's saying, is the function 1-to-1? So if you're looking for 1-to-1, remember, no repeated x's, no repeated y's. So if you look at your x's, I got no repeats there. Look at your y's, those are all different. That's great. So when it says, is it 1-to-1? The answer is yes, because there's no repeated x's or y's. Cool. So is the inverse of the function also a function? Well, let's quick finish this work first. So since the inverse does the opposite of what the function does, like if you plug in -4 and it gives you -2, over here, notice how you plugged in a -2 and it kicked back out the -4. So to fill in the blanks, you just have to find the one that it's paired with. So -3 should produce 0 back at you. 2, when you plug it in over here, should kick back out 1 where it started. And then you can see that it matches here. The 1 kicks back out the 4. So if there was no repeated x's or y's for the original function, then it would make sense that there's no repeated x's or y's for the inverse, because it's the same exact values. They've just swapped positions here. So when it says, is the inverse also a function? Yeah, absolutely. All right, there's still no repeated x values, right? And now, because it simply just said, is it a function? I don't actually care about the y's in that case. I just care that there's no repeated x values. If you want to happen to note like, hey, cool, it's 1-to-1, awesome, all right? Sliding on to the next one, it says the mappings below show a function is inverse. So again, here's your original function, and then the inverse over here will fill in some blanks. First question just asks, is the function 1-to-1? So here, all different x's, but I've got a repeated y value. So the answer is no, right? Because you've got the repeated y value of 2. So 1 goes to 2, 4 goes to 2. If you now fill in the blanks over here, since 0 went to -3, -3 goes back to 0. Since 1 went to 2, 2 should go back to 1. So now it's asking you, is the inverse a function? Well, no, because I have this x value of 2 now mapping to 2 different numbers. So the answer is no, because you have a repeated x value of 2, which should make sense because the y's here became the x's here. So the idea of what this is meant to show you is simply that if the original is 1-to-1, then the inverse is going to be a function. It'll have no problem passing a vertical line test or not have any repeating x values. Whereas if the original isn't 1-to-1, that means that your y values are repeated. And when they flip-flop and become the x values over here, you're going to have repeated x's. So, excuse me, when it says a function f of x will have an inverse f inverse of x, that is also a function if and only if f of x, the original, is 1-to-1. So I'm going to highlight that whole statement. That's going to be pretty key here. And if you don't have a highlighter, maybe you just star that statement. So now let's look at it graphically. So it says the graph of the original function from example 1. So back at the top of the page. is shown. So you just have all the points plotted here. So like the point -4, -2. There it is right there. Oops, sorry, I've got like a little fruit fly here or something. You've got the point 0, -3, you got the point 1, 2, and you got the point 4, 1. Okay. Then it says, note that the graph also shows the dashed line y equals x. So that's this guy right here. That's the dashed line y equals x. All right. It says write the inverse of the function as a set of ordered pairs and then graph them. So keep it easy. All we're going to do to go from here to here is we're going to switch, whoops, forgot a t there, switch the x and y coordinates. Right? So the point -4, -2 becomes -2, -4. 0, 3 is -3, 0. 1, 2 is 2, 1. 4, 1 is 1, 4. Just like it was back up in example 1. But now plot those. So -2, -4 is down here. -3, 0 is right here. 2, 1 is right here. And then 1, 4 is up top. So it kind of looks like a big old mishmash of points all over the place. But if we kind of maybe use some labeling here to show it, if I look at the original -4, -2, I'm going to circle it. And then -2, -4 right here. And I connect them. There was the original. There's its inverse. Let's do that again. 0, -3 is down here. Maybe I'll make a triangle little shape here. Make little codes. And then its inverse is -3, 0. Connect those. I've got 1, 2. Let's see. We can make a square shape this time. And then its inverse is 2, 1. Connects. And then the last one, maybe we can use like a little star shape. If I go over to 4, 1, and then 1, 4, its inverse, just so you can kind of see them visually. It just looks like fun after a while. What you can start to see is the point and its inverse, the point and its inverse. They're all on opposite sides of that line y equals x. And if you dig back down into your geometry memory right here, what you should hopefully recognize is that there is a relationship. When you have one equidistant on either side of that line, it means that we have a reflection over that line. So what we can say, all right, is that the inverse function, which is this guy, f inverse, is a reflection of the original function, which is f of x, over the line y equals x. And now, depends maybe who your teacher was. Some teachers always teach the reflections as having you like memorize the rules. This is one of the few times that I did think it was worth memorizing the rules. Otherwise, I'm terrible at actually memorizing those. But the rule for reflecting over the line y equals x, any like generic point, let's say a, b, was to simply flip-flop the values. So that was the rule itself. That was the rule in action. And so that's what happens when you switch the x's and y's, is that you end up with a graph that is a reflection over the line y equals x. So what I'd like to do is look at some of the algebraic work and then also graph it to kind of see how those go hand in hand. So flip it on over to the next page here. And it says finding the inverse of specifically a linear function. Now to save you some time, all the steps are right here. Hopefully you can read it a little bit easier on paper there. So wherever there's an f of x, we're going to sub back in just a plain old y. And then here is the key step. We are going to switch x and y. Since the inverse actually switches your inputs and outputs, we're going to you're actually going to calculate or determine an inverse equation. Right? So we'll start with the line, or the function, excuse me, f of x equals 3x minus 4. So this is just a basic old line. So I want you to start by putting in place of f of x a y, and then we have 3x plus 4. That's step one. Step two, switch the x equals 3y plus 4, and now we rearrange. So we're used to having a y equals. So let's make it a y equals. So subtract 4 on over, and then divide both sides by 3. And because it drives me bonkers to have the y on the right, I'm going to switch it and put the y on the left. And then I can either keep it as x minus 4 over 3, or if you'd prefer, you could break it apart and you could make it, y equals x over 3 and then minus 4 over 3 so that it looks a little bit more like mx plus b. Last step, wherever y was, that is now the inverse equation, so we can replace it with f inverse. So that's going to be the equation of the line of the inverse of the original, which was f of x equals 3x plus 4. Now, you can try to maybe go mx plus b style and graph that, but it's not easy with a starting point of -4/3. So a much simpler way to graph this, other than getting out your graphing calculator, which you could absolutely do that too, is actually just to pick a couple of points and then swap out the x's and the y's and have them switch place. So when you think about the original function, y equals, 3x plus 4, if we go to graph that guy, slope is going to be up 3 and over 1. Y-intercept would start up at 4. So I can come up 1, 2, 3, 4 and plot that. And then I could either count up 1, 2, 3 and over 1, which is going to run us a little off the graph, or go down 1, 2, 3 and left 1 and then repeat. All right, so let me grab, I happen to have a straight edge sitting next to me. Hopefully you have something that you could use or just draw as neatly as you can. All right, that is my original f of x right there. All right. What I want to do is to be able to graph, oops, let me double check something here. There we go. To be able to graph the inverse, let's just take a couple of points that we just came up with. You guys might hear Teddy barking in the background there. All right, so we have the point 0, 4. And I have the point, let's say, -1, 1. Maybe we'll use one more. Here's the point -2, -2. Cool. All right. If I want to plot them as points on the inverse, switch the x and the y. So this will now become the point 4, 0. That will become the point 1, -1. This will actually stay the point -2, -2. All right, let's plot those. So if you have a different colored pen or pencil, here's a great place to use it. So over to 4, 0. There we go. 1, -1. And then -2, 2. So what you're going to get should be a nice line here. So all those points are collinear, should line up beautifully. And it should look as if you took the original f of x and just folded it right across that line. So notice there's that nice dotted line right down the middle of y equals x, and it's perfectly symmetrical over it. So you can see it algebraically, you can see it graphically, how it's all going to relate to one another. What I'm thinking is let's save this second one for a little recap in class. So right here for part B, you can write yourself that note that will recap that guy. And then let's jump to that last page. Last page. That's always exciting when we hit the last page here. All right. For evaluating inverse functions, there are 3 examples here. If we can squeeze them all in, great. If not, no big deal. To be able to evaluate an inverse function, let me give you an example of what I need. So f of x equals 3x plus 7. I'm going to give you that linear function. First thing I want you to do, I want you to find f inverse, and then I want you to evaluate f inverse of 34. Okay. So this is some good practice right here. So first thing, just like it said on the other page, you're going to sub in y for f of x, and then we're going to swap x and y here. So x is going to be equal to 3y plus 7, and now rearrange. So let's subtract 7 over, divide both sides by 3, and I get y equals x minus 7 over 3. Last thing, go ahead and put f inverse back in there. So here is the inverse function to this guy. So if we graph them, one will be the reflection of the other over the line y equals x. Easy, all right? Part 2, now I want you to evaluate f inverse of 34. So all I'm asking is for you to take that function and plug 34 in place of x. So 34 minus 7 over 3. If we do a little mental math, or you could simply grab your calculator, that is up to you. We get 27 over 3. That's going to come out as 9. So we've got the first part. We've got the second part of it. What I would like to show you is that there is a little bit of a shortcut if I hadn't given you step 1 and I had just said evaluate f inverse of 34. Right? So here is your little shortcut. Right? So if I said, maybe we'll put the word here first, evaluate f inverse of 34 and just said go, what I want you to remember is that when we see f of x and then equals y in the original, you're plugging in an x, you're kicking out a y. If I ask you to do f inverse of a value, what that means, that's the same as if I really plugged in y, right? Or started with the y and then found the x. So this is the same as saying, let's use a different variable so I don't confuse you. If that was a, saying f of what x value would be equal to a. So in this case, this is the same as f of what x value comes out to equal 34. Right? Because the x value for the inverse is the same as the y value of the original. All right, so go back to the original equation. 3x plus 7, set it equal to 34. All I would do is subtract 7 from both sides. There's 27, divide by 3, and 9 would be my answer. So if we can understand that relationship between the original function and the inverse function, then you can kind of play around with what's easier. Could you always default to just finding the inverse relationship and then plugging in? Yep, but it's a heck of a lot faster to never have had to solve this in the first place and to just simply say, oh, if you're asking me to evaluate this, it's the same as setting the original just equal to that in place of the y value and then going from there. I think let's save the last two, so examples 2 and 3, for our recap. And then make sure, I hope you were listening and paying attention closely so you can answer that follow-up question now. Thank you.